Today we are going to be looking at substitution as a technique to solve certain equations. So let's take a look at this example. So as you can see, it's quite a complicated equation, right? We have numerous terms over here and some terms under a square root, and it looks kind of difficult to deal with at first. But what we can notice is that what we're trying to avoid is this square root expression right here. Even more to that point, we have x squared plus 4x here, which is a part of this square root expression. So let's see what happens if we can assign a variable to this square root expression right over here that'll allow us to solve the problem. So let a, for example, equal the square root of x squared plus 4x plus 5. Now let's see what this will allow us to do. Well, if we want to get the x squared plus 4x term outside of the square root, then of course we need to square it, right? So we have a squared is equal to x squared plus 4x plus 5. Now we realize that a squared minus 5 is equal to x squared plus 4x, right? And now we can actually substitute this for this, x squared plus 4x. Also, since our square root expression was originally, we defined that to be a, we can also substitute a over there. So let's see what happens when we do that. A squared minus 5, and then we also want to substitute a for this square root expression, so we get minus 2a. And then finally, we also have this plus 6 at the end, and that is equal to 0. Now you'll notice something. If we simplify this, we get a squared minus 2a plus 1 is equal to 0. And at this point, you probably see this factorization right over here. This is just a minus 1 squared equal to 0. And now we automatically know what a is. It's 1. And now we can simply go back here, look back at our definition of a, and put 1 there, and we get 1 is equal to the square root of x squared plus 4x plus 5. Now we can square both sides. 1 is equal to x squared plus 4x plus 5. Subtract 1 on both sides, which will give us 0 is equal to x squared plus 4x plus 4. And now, at this point, we can recognize that x squared plus 4x plus 4 is simply x plus 2 squared. And that gives us x is equal to minus 2. So notice what we did. We noticed that there's some similar terms, right? This x squared plus 4x and this x squared plus 4x over here that inspired us to look for substitutions. Then we substituted for the term that was the most annoying to deal with, which is this square root term right over here, and that helped us solve the equation. This problem is from the AIME in 1990, and it is problem 4. And this is along similar lines, right? Because we notice that x squared minus 10x, x squared minus 10x, x squared minus 10x. So that is definitely telling us to do something with substitutions, because we don't want to multiply by a common denominator and simplify all of that. That often gets way too complicated. So all we have to do is pick one of these to choose as what we want to substitute. Often a useful thing to do is to pick the middle term, because then you get something that is a little bit greater and you get something that is a little bit less, at least in the denominators. So let's pick x squared minus 10x minus 45 as what we want to substitute. So as usual, we let a equal x squared minus 10x minus 45. Now we notice, well, what is this in terms of a, and what is this in terms of a? Well, this is a plus 16. This one is a minus 24. And this already makes us feel like we're on the right track because 16 and 24 are relatively nice numbers. And of course, this one we defined just to be a. So if we write down our new equation, we have 1 over a plus 16 plus 1 over a minus 2 over a minus 24 is equal to 0. So we get 1 over a plus 16 plus 1 over a is equal to 2 over a minus 24. Now, this is much simpler to take the common denominator, so let's do that. We cross multiply, so a times 1 plus a plus 16 times 1 over the product of these two, so that is a times a plus 16. And that is, of course, equal to 2 over a minus 24. Now notice this part is 2a, and we can actually divide out by a 2 on both sides, because then if we divide out by this 2, right, so we get a 2 here, and this becomes an 8, and this becomes a 1. So a plus 8 over a times a plus 16 is equal to 1 over a minus 24. And now we can just cross multiply again. So that'll give us a minus 24 times a plus 8. That'll give us a squared minus 16a minus 192. On this side, we'll have a times a plus 16 times 1, which is simply a times a plus 16, which is a squared plus 16a. Now, as we can see, this a squared term and this a squared term nicely cancel. So now we can move negative 16a to this side, and that'll give us negative 192 is equal to 32a, which finally gives us a is equal to negative 6. Now remember, that's not quite what we wanted. So if we look back at our definition, we have a is equal to x squared minus 10x minus 45. And now we can substitute what we got for a, which was negative 6, back into this equation and solve for x. So let's do that. So we have negative 6 is equal to x squared minus 10x minus 45. And then we can add 6 to both sides and get 0 is equal to x squared minus 10x minus 39. And we see that 39 is 13 times 3. So we can factor this nicely. 0 is equal to x minus 13 times x plus 3. X is equal to 13 because they're looking for only the positive solution. And as usual, you can check to make sure everything works and we didn't get any extraneous solution anywhere. So as you can see, this followed a very similar idea. We're looking for ways that we can substitute values for more complicated expressions in order to first solve a simpler problem and then finally solve for the more complicated expression. So this is another problem from the AIME 1991 problem 7, and this definitely looks like a complicated expression. So we want to find a squared, where a is the sum of the absolute values of the roots of the following equation. So the key idea here is that there's a repeating pattern to this. So when there's a repeating pattern, usually you can substitute for that repeating pattern. So one thing that we notice is that the infinite version of this, where instead of x it just keeps going on and on and on, would be a solution to this equation. So that means that this value of x, whatever values of x satisfy this, must also satisfy x equals root 19 plus 91 over x. So that's the key here. This is a substitution, right? Because we saw that an infinite version of this, instead of x here, would just continue on and on. if we substituted that entire part for itself back again, which is x, we would just get x is equal to root 19 plus 91 over x. So make sure you understand why that substitution worked. So now we just want to solve this equation, and that'll give us x squared if we multiply by x on both sides. That'll give us x squared is equal to x root 19 plus 91. So x squared minus x root 19 minus 91 is equal to 0. And we can use our handy dandy quadratic formula. So x is equal to root 19 plus or minus square root of this coefficient squared, so 19, minus 4 times negative 91, 364. And of course, we want to divide that by 2 times the first coefficient, so that is just 2. Now, these are the possible values of x, but they want the absolute value, the sum of the absolute values of the possible values of x. So one possible x, which is positive anyway, so the absolute value is just equal to itself, would be root 19 plus root 19 plus 364 over 2. So that is one possibility. And obviously the absolute value of that is equal to itself because it's positive. However, if we look at the other possible value, which is root 19 minus root 19 plus 364 over 2. So since this entire expression is negative, the absolute value is going to return the negative of this value. That means that instead of a minus here, there would be a plus, and there would be a minus for this. So we're going to add these, right? And that means this will cancel out. It'll just give us root 19 plus 364. And what did they ask? So this is equal to a. What did they ask? They asked a squared. So a squared would give us 19 plus 364, which gives us 383. And that is our answer for this problem. And as you can see, that's quite an interesting problem, because what you have to realize is that this repetitive nature of this problem makes us want to do some sort of substitution, which will allow us to get this. So let's look at this problem, which is quite interesting. This is also from the AIME from 1989, and is problem 1. So here, notice that we have 28, 29, 30, 31, and we just want to compute the value of square root of that plus 1. Okay, you could expand this, multiply it out, add 1, and take the square root, and that would be okay, but you wouldn't learn anything from that, right? So instead, what we're going to do is, since this is a progression, an arithmetic progression, we're going to substitute a variable for a constant. Now that seems weird, right? Because we're losing information. But substituting a variable may allow us to do some factorization or some pattern that we may notice. So let's let some variable, I don't know, n, for example, equal 28. Our expression now becomes the square root n plus 3 times n plus 2 times n plus 1 times n, and then plus 1. Let's multiply this one with this one, and let's multiply this one with this one. N times n plus 3 is close to n plus 2 times n plus 1, while n times n plus 1 is less close to n plus 2 times n plus 3. So let's do n plus 3 times n first, which is n squared plus 3n. N plus 2 times n plus 1 will get n squared plus 3n plus 2, and of course we have to add 1. Okay, that's nice, but what are we going to do here? Well, now we notice something quite interesting, because n squared plus 3n is in both of these, right? So we have an n squared plus 3n here and an n squared plus 3n here, And what do you want to do when you see something like this? That's right, you want to substitute for that. A, if we let A equal n squared plus 3n, let's actually write that so we don't forget. So A is equal to n squared plus 3n. And now this gives us A times A plus 2 plus 1. And let's expand this and see what we get. So that gives us A squared plus 2A plus 1. And now we see what's happening, because A squared plus 2A plus 1 is simply equal to A plus 1 squared. So this gets rid of that, and we just want to find A plus 1. In other words, we want to find n squared plus 3n plus 1. That's our answer. So what was n? That was 28. So we wish to find, so our answer is equal to 28 squared plus 3 times 28, 3 times 28 plus 1. If we factor out a 28, we get 28 times 28 plus 3 plus 1, which gives us 28 times 31 plus 1. And if we calculate that, so 31 times 28 is equal to 8, 24 here, 62 here, which gives us a final answer of 868 plus 1, which is 869. So yeah, make sure you don't forget that plus 1 over there. So that gives us 869. Now, that really shows the power of substitutions, because we did not recognize that this expression would turn out to be a perfect square immediately until we looked at the substitution for A is equal to n squared plus 3n. So hopefully you found that interesting.